Welcome in this video, where you will see how to implement a simple PK modeling workflow in Monolix 2018 with the example of warfarin. Let's open Monolix and create a new project. Creating a project in Monolix is an easy process that is guided with the apparition of a new tab for each step. The first step is the definition of the dataset. I begin by loading the dataset in Monolix. Each column of the dataset needs to be assigned a type. Here they have all been assigned automatically because they have standard names in the header: ID, time, amount, DV for observations, DVID for observations ID. There are two observations ID here, one for PK and two for PD. Weight, sex and age are recognized as covariates, continuous for weight and age, and categorical for sex. Of course, these types can be changed if necessary. Then I can click on Accept. Before going on, let's first explore this dataset in the data viewer. A set of plots can be seen in the data viewer. First, we see the continuous observations of concentration of plasma warfarin as a spaghetti plot against time. We can check that there is no outlier. Selecting information displays some figures of the dataset, such as the number of subjects, 32. There is also one dose by subject that we can highlight by selecting dosing times and hovering on the curves. By choosing the log on the y-axis and zooming, we can already notice that a one-compartment model with linear elimination seems adequate to fit this dataset. It is possible to split or filter the plot using the covariates. For example, I can create two groups of individuals according to the weight with equal count, and stratify the data from these two groups either by coloring or splitting. Here it looks like weight could have an effect on the concentration of warfarin. Let's now have a look at the effect versus time. The PD is the prothrombin complex response. It is a percentage and it is inhibited by warfarin. We can also display the effect with respect to the concentration in order to have an idea on how to model the interaction between the PD and the PK part. The plot is created with interpolation between data points. The response seems indirect. Finally, it is possible to display covariates on the axis to check for correlations. With weight versus age, we see no correlation. With weight versus sex, on the other hand, we see the expected correlation. With sex versus sex, we see a bar plot with the number of each value across the dataset. There are only 5 values for 0. As a conclusion, exploring the dataset suggested to use a one-compartment model with linear elimination for the PK part, an indirect model for the PD part, and allowed to identify a correlation between the covariates weight and sex. In the rest of this video, we are going to focus on modeling the PK part. For this, let's go back to Monolix. For the next step, I have to define a structural model. This can be done by browsing a personal file, loading a model from the library, or writing a new model with the editor. In this example, we are going to pick a model from the library. There are 5 libraries that contain lists of standard models for PK, for PD, joint PK-PD, target mediatic drug disposition or TMDD, and time to event or TTE. We are going to choose a PK model. As seen in the data viewer, we will first try an oral model with no delay, a first-order absorption, one compartment, and a linear elimination. 2 equivalent models are available, the first one with the clearance among the 3 parameters, the second one with the elimination rate. Let's choose, for example, the first one. The next step is to choose initial estimates for the population values of these 3 parameters, Ka, V, and Cl, such that the population prediction in red roughly fits the individual data in blue. The goal here is to start from a point not too far from the solution, so that the convergence will not take too long. This is a step where the modeler can potentially bring some knowledge of the system to guide the estimation. I will choose to increase V to 10 and decrease Cl to 0.1. When I'm happy with the values, I can accept them with set as initial values. The Statistical Model and Tasks tab can then be used to run some tasks to evaluate the full model on top and adjust the statistical model, composed of the observation model in the middle and the individual model on the bottom. As a first step, we aim at validating the structural model. Therefore, we first keep the default statistical model. Note that the observation model relates the prediction to the observation with a residual error model. The default error model is a combined model whose formula can be displayed by clicking on Formula. There is an additive and a proportional term. The default individual models include log normal distributions for all parameters. On the right, it is possible to define correlations between parameters or covariance effects. For now, let's keep this empty. My model is now ready for estimation. Before running, I'm going to save my project as a text file that contains all the information in the project with the MonolixSuite extension. Saving now is important because when I run some tasks, the results of the tasks will then be saved in a folder next to the project file. I'm going to run and explain each of these tasks one by one. The first task estimates the population parameters with the algorithm SAEM. On this pop-up, we see how the parameter estimates evolve over the iterations of the algorithm. The algorithm works in two phases. Before the red line, the parameter space is explored during the first phase. When the exploration converges, there is an automatic criteria to switch to the second phase, to stabilize towards the local minimum. The results of the estimations are now available in the tab Results. Then I can estimate the empirical bias estimates, or EBEs, which are the most likely parameters for each individual. They are taken as the mode of the individual conditional distributions. A summary of the results is displayed here in the tab Results, Individual Parameters. The next task estimates each individual conditional distribution by sampling a set of values from the distribution with the Markov chain Monte Carlo procedure. A summary of the conditional means of the distributions is now available here. The results of this task also increase the performance of model diagnosis and in particular avoid the phenomenon of shrinkage that can affect EBEs. I can then estimate the standard errors for the population parameters. If the model is complex, a linearization method can be used to reduce the computation time, but here I can use the exact model. Standard errors are then computed with stochastic approximation of the Fisher information matrix. The correlation matrix of the estimates is now displayed here in the tab Results, Standard Errors, as well as the standard errors that can also be seen on the table of the population parameters. The algorithm SAEM does not require to compute the log likelihood, so the next task allows you to estimate it for the comparison of this model to more complex models later on. It can be computed either via linearization, which is faster, or via importance sampling, which is more precise. The result is then displayed here, along with other information criteria, the IKK information criteria and the Bayesian information criteria. Finally, I can generate diagnostic plots to assess the quality of the model. They now appear in a tab Plot. A list of plots have been generated automatically. For instance, you can see the individual fits or the observations versus predictions. On this plot, I can choose a log-log scale to focus on the low observations. I notice that several observations are over-predicted. For example, for individual 12, individual 14, individual 8. They all correspond to low times. We can see what is going on for these individuals on the individual fits. Let's zoom on the first times for all plots. We can see that the first observations are over-predicted, for example for the individuals 12 or 8. This suggests to add a delay for the absorption in the model. I can then go back to the Structural Model tab to choose another model. The model that I want is available in the PK library by choosing oral, a lag time, a first-order absorption, one compartment, and a linear elimination. I now have a new parameter T-lag to estimate. Since the project has been modified, I will save it under a new name. Now that I have explained all the tasks, I can run them all in a row by selecting them and clicking on Run Scenario. Again, a pop-up window allows me to easily track the progress of each task. Once the plots have been generated, I can check that the over predictions on the plots of observation versus predictions are gone. There is no longer any clear misspecification. I can then consider that my structural model is validated. Let's now look at correlation plots to adjust the statistical model. On the plot individual parameters versus covariates, the transformed parameters in Gaussian space are plotted against the covariate values. This is useful to see correlations between parameters and covariates and identify covariates effects. Notice that the individual estimates that are used here are sampled from the conditional distribution, instead of taking the means or the mode of the conditional distribution. This is critical because it is known that the plots using the mode or mean of the conditional distribution can show non-existing correlations. On the contrary, sets of simulated parameters from the conditional distributions are reliable estimators. Here we can see correlations between log V and weight, as well as sex, and also between log CL and weight, and a small correlation between log CL and age. Correlation coefficients can be displayed by clicking on Information. Moreover, the detailed statistical tests for correlations between random effects and covariates are available in the tab Results and Tests. We can see from the p-values that there are two significant correlations, one measured by the Pearson test between weight and V, and the second one measured by ANOVA between sex and V. Let's first add an effect of weight on V in the statistical model. Before doing this, let's keep the estimates from the first run as initial values for the next one. This will decrease the time of convergence. In the tab Initial Estimates, I just have to click on Use Last Estimates to store the previous solutions here as initial estimates. I can now add the covariate effect here. Let's first display the formula of the individual model to see how it will be affected. By clicking here, I will add linearly the variable weight to V in the transformed parameter space, with a new parameter beta V weight. However, I would prefer a power law between V and weight, and I would like to center weight around its mean. This means that I have to transform weight. By clicking here, I can create a new continuous covariate. I will call it Tweight, for instance, and define it with a formula, log of weight over a typical value. If I am not sure what the typical value should be for my covariate, I can hover on its box to see the statistics across the dataset. I will use the mean 70 as the typical value. I can now use Tweight instead of weight. I can see now that taking the exponential of this formula will recover the usual formula using the power law, because Tweight is the log of weight centered by the mean. Let's save this new project. I can then run all the tasks to estimate the parameters, and in particular the new parameter beta. The parameter beta has been estimated. A wild test has also been computed with a p-value displayed here. It is low, which means that it confirmed that the parameter beta is significantly different from 0. Moreover, the value of omega v has decreased, because some of the variability of v across the population is now explained by weight. Finally, I can check that the log likelihood, BIC and AIC, have decreased, showing that the fit has improved. On the plot of individual parameters versus covariates, I can choose the random effects to check if we have remaining correlations between the random effect and the covariates. I can see that there is no more correlation between V and weight, and also between V and sex. This is because weight and sex are strongly correlated, as we have seen on DatExplore. There are, however, remaining correlations between CL and age, as well as weight. When I check the statistical tests, I see that only the correlation between weight and CL is significant. I can therefore proceed to an additional run of the model with this covariate effect. First, I use the last estimate as new initial estimates, then I change my statistical model, and I save the modified project before running. As before, I have several ways to check that the covariate effect is relevant, so let me show them a second time. I can look at the correlations between parameters or random effects and the covariates on the plots. I can check the detailed statistical test, where I see that the wild test for the new parameter beta is barely significant. And finally, I can check the information criteria. They have all decreased a little, so it confirms the improvement of the fit and the relevance of the covariate effect. Let's now have a look at some advanced diagnosis plots. With this icon next to plots, I can choose the list of plots to generate. Instead of only the default plots, I'm going to select them all and then run the task again. In the tab Plots, I can now see additional plots, for example the VPC. The goal of this plot is to compare the empirical percentiles that come from the dataset to the prediction intervals for simulated percentiles that come from the model. There are few discrepancies highlighted in red, which means that the prediction power of my model is high with respect to this dataset. Let's have a quick look at a few other plots that are available without going into the details. There is a plot for a numerical predictive check, a plot for prediction distributions, and also plots to investigate the residuals, where I can easily identify which data points result in the highest residuals. There are even more plots than this. You can find a full description on our online documentation. Finally, I can check possible correlations between pairs of random effects on the plot correlations between random effects. Here again, the correlation coefficients are available by clicking on Information, and the associated p-values are also displayed in the statistical test. Here no correlation is significant. Let's try anyway to add the correlation between V and CL in the model to make sure. To do this, I will first use the last estimate, then add the correlation here, and finally save the modified project under a new name. Before running the scenario. I am now going to estimate an additional parameter for the correlation between V and CL. I can check its value in the tab Results. I see that the relative standard error is high. This is because the correlation is still not significant, as I can check in the statistical test. Now that the correlation is in the model, the p-value appears in red. Moreover, when I look at the log likelihood, I can notice that both AIC and BIC have increased a bit. I can then conclude that the correlation between V and CL brings no improvement to the model. In conclusion, my final model for the PK of warfarin has one compartment, a delayed first-order absorption, a linear elimination, and a covariate effect of weight on the volume as well as the clearance. In the next video, I will focus on the PD part of this dataset and show you how to do joint modeling in Monolix. Remember that you will also find more information on any part of the modeling workflow on our documentation in the tab Welcome, Documentation, or online on monolix.lixoft.com, including how to model any kind of data, details on the algorithms and tasks in Monolix, or on diagnosis plots. I hope that you enjoyed this video. Have a good day!